Okay, so our article reports on a real-time method to predict protein functional transitions using nonlinear normal model analysis. Our main results are summarized in figure 2. So we tested the method on 155 transitions using the 10 lowest frequency modes. And here is what we predicted for the calcium ATPase pump. So you can see that the transition is large, about 13 angstrom, and it's very smooth and the structure is very well preserved. Now, if we do this with linear normal modes, we obtain a lot of distortion, in particular in the colored region, which corresponds to the highest displacement. We can quantitatively assess the quality of the predicted conformations by looking at the overall G factor computed by Procheck. So if a conformation is above the red dotted line, then it means that it looks like a real experimental structure. So we can see here that the distribution obtained with NOLB is mostly above the red line, and it's significantly shifted toward higher values compared to the distribution for the linear modes. So our ensemble of transitions is divided in 3 benchmark sets, colored in different gray tones here. And some transitions are very localized, meaning they involve very few residues, for example, just a loop. And some of them are highly collective, meaning that most of the protein moves. So what we can do is assess the transition coverage with respect to this collectivity. The coverage reflects the amount of the transition that we are able to predict. So we compare here our method NOLB in y-axis with the linear modes in x-axis. What we can see is that we almost systematically have a better coverage than the linear modes, and an important fact is that the improvement is sometimes very high, especially for some localized and mildly collective transitions, so in gray and in blue. So these results challenge the long-standing belief that normal mode analysis cannot be used to describe localized motions.